So Python bindings they were not introduced for the GPU version, but first for the CPU version. And but we use them quite heavily for the GPU version now as well. So I actually don't know how much you use them on the CPU still. But so kind of our motivation was that, well, in general, it's a little bit easier to write Python scripts than it is to write C++ apps. Especially for the, if you know, for the younger generation, often there may be more experience with that. And actually, what I find, as long as it works, I find the installation process via the Python interface a little bit easier because it can theoretically take care of a lot of things. And then the main motivation for us, why we wanted to also write the Python bindings for the GPU code, was that we wanted to couple it to other codes. And, like you have a C++ code, and then you have another code that's a Fortran code, and you have to kind of make them talk to each other, and then compile them together, and link, and all this stuff. Of course, it is doable, but it's not straightforward necessarily. And also, I think very prone to break. So our idea was that because we had written in a previous LBM code, we had written all the extra line things and everything directly into the LBM code. But then you have to do all the reading of file formats that are, kind of verbose. If you, have a full configuration of a wind turbine, and there's all these extra modules that you all need, such as the controller and so on. Like doesn't have anything to do with VirtualFluids. And I don't need to pass this through Martin to get it merged. So we decided, and then they don't see what we do there. So we decided to keep it separate then when we switched over to VirtualFluids and have one module that we call the wind farm interface, or Wi-Fi, that does all the turbine stuff. Everything that's related to a turbine, that's reading airflow data, controller, coupling to aeroelastics, anything you can imagine, all of that in Wi-Fi. That is mainly written in Python, but where the core parts, for example, the computational forces for the actual line, that's on the GPU. So it's still very fast, and we can also run this in separate now, because then everything else is, like all the fluid stuff is in VirtualFluids, but VirtualFluids doesn't need to know anything about the turbine. What VirtualFluids knows is there is a point here that has a force, and I would like to know the velocity of that point also. That's it. So it's very light on the VirtualFluids side. And we also see that because the way that we did it is, because of course VirtualFluids already existed as these libraries, so you only have to you wrap the outermost shell, so to speak, is a bit of Python. But everything, like the time step and so on, is run, that's still the C++ program that's running. So we see no difference in performance. So we get something that's easier to couple, but we don't have any penalty except the programming penalty. It's just work, it's just my time, but that's very cheap. So that is kind of the motivation, and why I'm personally a big fan, and since I'm a big fan, I'm also, I would say, probably the most responsible, have the main responsibility for the Python bindings at the moment. So when something breaks, I was probably the one to break it, but also I'm the one to fix it. All right, how do we do this? So we generate a Python module called PyFluids, and you can either have and that then can contain the different libraries that are part of VirtualFluids. So it contains the LBM library, it contains it can contain the GPU library, and can also contain the CPU library. And then we use PyBind11, which is a library to generate these bindings explicitly. So we generate a C++ or like a compiled library that you can just directly call from Python, but it's directly exposed to Python. So you don't have, as we talked about yesterday, that how you do it on your side in Ellipsis apparently, that you have a Python interface to the direct C++ code, but it's kind of the other way around. We define the interface in C++. We never have to define it in Python. We just directly call it from Python. I think that has the advantage of that if something breaks, if there's a mismatch between if you update the C++ code that calls, and that where the function or the method is bound to a Python binding, then it directly breaks. It tells you so you don't, you find out faster. And I think actually it is easier to write it in this way. It's more explicit, it's more verbose, but you of course have to do it also all the time. And the compilation process is of course more complicated because now you're compiling it. And so there's a separate piece of, there's a separate folder in VirtualFluids that's just called Python bindings, and that's where all these things are defined. And then something that we also introduced recently was that we provide what's so-called stubs, so that all the Python tooling actually knows. So because normally it can't look into the compiled Python library in the compiled C++ library. It doesn't know anything about it. It can't understand that. But these stubs, they tell it, they pretend to know what it's in there. I will show you in a second how this is actually done. But that is the point where it's that often the synchronization is not automatic, right? Because we have to write these stubs manually, and we don't see if that doesn't align anymore. So but then Python will tell you that you tried to do this, and even though it told you it's gonna be okay, it wasn't, and it will just not run. Okay, that's how we do it. There's a couple of caveats, especially when you're running you can also run multi-GPU with the Python bindings, no problem. But especially when you're coupling it also to, because now we're really, really at the edge of what people do. So now we're using Python bindings to run MPI and CUDA all at the same time in multiple processes eventually, because when we do it with Wi-Fi, then we run it in parallel. So we're really mixing a lot of things together, and it's very prone for errors, of course. So I figured it out once, and I just do it, like I don't change the setup anymore, because this is how it works. But but when you want to run it, you have to make sure that you have an MPI for Pi that is bound to the same MPI as you use for building VirtualFluids, and you have to use the multiprocess. If you want to run in parallel on Python, you have to always use the multiprocessing library, and making that work with CUDA also with Wi-Fi then is a bit tricky. But there's an example also in VirtualFluids on how it's done, and that one works. So take that one and extend it. Because this is also, we're really outside of well-documented area. Like, no one hates themselves so much that they do this. All right, so that is the theory behind it. Well, theory may be a strong word. And then here we have an example. So in Python, the modern way to define a Python package is to define a pyproject.toml file that kind of gives the configuration. And this you also find at the top level directory of VirtualFluids. So this defines what we built. So we use what's called scikit build core as the backend. That will then call cmake and handle all the making sure that the Python is working with the cmake and with the library and all of that. This takes care of this, and it actually does it really well. And then it will generate a Python package or library. Those are the same things in Python world, called PyFluids. And then we have a little bit of configuration. And so we can actually define directly in this PyProject TOML, we can define the CMake arguments that we usually define on the command line, right? Or we call CMake dot minus D VF enable GPU, for example. You can directly define it in the PyProject TOML as these CMake.defines. Now I've set them. Then this is not what the vanilla, like the normal version looks like. I just set them now to specific values. Usually we only the version that you find on the remote just looks like this, right? It just tells you build the Python bindings. But because I want to build I know that I'm going to build the GPU version now, I set all these other flags as well. And because I'm now working on the on the Docker, I also want to use unique make files, so then it's compatible also to the normal build. All right, so this is kind of where you configure the run. You can also configure the building directly on the command line with pip, and we're gonna use pip to install it. So we do normal pip install, and then we want to install the package in the directory that we're currently in, and then there's the pip in the Docker is kind of old, so it doesn't support this yet, unfortunately. But if you have a newer pip, you can do -c and then pass these cmake.args. No, like this. cmake.args, and then all this defines that you would usually give. So, for example, dvf enable GPU equals on. So this way you could also run it. But unfortunately, you need a pip that's newer than version 25, and we have 22 on the Docker. So that's why I wrote it into the PyProject.toml. That always works. So if I now install it, and I can pass the -v flag to see a bit more what's going on. You see here first, we download like a bunch of stuff. So this is pip handling the dependencies of what we want to build. And then we see scikit build core starts to set up the CMake. And then here, this is the normal output. Then we are just running CMake on the project. So this is the very normal CMake being called in the background, and also directly building it. And then it did all of the compilation, so on and so forth. And then here, the line that we want to see, we successfully installed PyFluids. And then your heart rate can go down again. So there's a couple of example scripts in the Python directory. So I'm going to talk about the Python bindings where we define them in a second, but at first showing you that it's what you can do. So we have, for example, an actuator line example, and now you see also my linter is highlighting the PyFluids correctly, and it tells me stuff about it. Those are the stubs. Because if I didn't have the stubs, it would just be white, and it wouldn't know anything about it. So we don't have any. You wouldn't have any autocomplete and so on and so forth. But with the stubs, you have the autocompletes. And then we try to keep the bindings very close to the original. So the structure and the naming and everything is very, very similar. Is as identical as it can be. Between the C++ and the Python versions. It's not possible to make it completely identical, but it's very, very similar. So then we set everything up. And for example, one of the, where it can't be the same between the C++ and the Python version is when we call the configuration file, because we can't we can't use the templates. So we have to find each template explicitly. So it actually, in the end, it looks almost the same, right? And we also, when naming everything, we followed the Python convention of using snake case and not camel case as is in the C++ version, so that it looks very Pythonic. So yeah, you know, it's really the same. This is actually a bit of a different. The app is not exactly the same as the actuator line app.
If the thing, okay, it doesn't of course now too stupid, but apparently it's clear when it's called Python, then it must use snake. Okay.
I never thought about that, but yes, yes, exactly. Of course, it's nice.
Okay, so everybody knew this.
No, that's why you're the theoretical person. You know, you see these things.
You sometimes need to be told the obvious.
Mm. So yeah, we said this time we actually set up a boundary layer flow with an actuator line in it. So you know, this really it's almost one by one the C++ app. And then yes, exactly here, this bit. So we actually managed to do it that you can define the these initialization functions. I have it in the comment here. You can define it in Python and then pass it to C++ to run the initialization of the macroscopic quantities. That works. The problem is just it's extremely slow, because you call a Python function for every single node in series. So and you know, you have to evaluate, especially in this case, all the sines and cosines and so on. So we provide a bunch of pre-configured initialization functions to make it faster for kind of the typical cases that the people that use the GPU version use. AKA, it's the log law and it's the perturbed log law that we saw in the previous session. And then here we have the actuator farm standalone. So this is again, you know, this is not coupled to Wi-Fi. And we do exactly the same things as we did before, and then we call run, and then we run it. And now we try to do that. And
didn't you uncomment?
No, I left it. Commented.
Because it didn't save.
Yeah.
Right.
So now we get the, you know, it's VirtualFluids. It does what VirtualFluids does. It's the normal VirtualFluids output. So I run here, and now I don't know when I'm going to write the performance, but for example, we can check how we're doing on the GPU. We're using 99% of the GPU, so we're not waiting on the CPU Python bit. We're fully using it to its max. The only downside with using Python is you can't cancel the run, because it's stuck, it's in the C++ function and running the C++ functions, and the kill call doesn't go through. That is really the downside. So you have to kill it by hand. Then it's done. And I think I manage. It's rough, but compared to the other hardships, it's okay. Yeah. As I said, we also have coupled this to this Wi-Fi that I mentioned before. So now Wi-Fi is not installed in the Docker container, but there is actually a Docker container that I think Anna created, where you install Wi-Fi directly with it, and Wi-Fi depends on this QPy stuff. There you also find the link to Wi-Fi. So I don't have this container, so I can't run it at the moment. But here you see, like one of the things is that you have to define a main function, and you must call the main function in the end. Like that's kind of the difference that if you couple it to Wi-Fi. And finding that out takes a lot of time. And what you do here is that you just create this turbine from a farm. It's maybe not the best model, the best naming, but instead of generating a normal actuator farm standalone, we have this kind of wrapping function in Wi-Fi that we create a subclass of the this actuator farm as a Python class, and then we just pass that into VirtualFluids, and then that runs. And now it does all the communication of data and so on and so forth. So you as a user actually don't have to worry as much. So this takes care of all of that. So this is how you'd run VirtualFluids also with the wind turbine, with a proper wind turbine that doesn't have just elliptic blades. But you can, whatever you have implemented in the coupling is what you have. All right, so that's the use. Yes.
After the line is actually still like the turbine, like the lift and drag calculation, for example, like points and so on. That actually is happening on the C++ side, right? Or is that happening on the Python side? And then
So you mean for Wi-Fi?
yeah, for Wi-Fi. Yeah.
For Wi-Fi, the computation of everything happens on the GPU. So we don't even copy the memory, we just pass the pointer to Wi-Fi, where we have like we have a buffer, basically. We interpolate the velocities in the actuator line with this trilinear interpolation into one array. On the GPU, we just pass that pointer to Wi-Fi, and then Wi-Fi takes that pointer and computes the forces on the GPU.
Okay, that's on the GPU.
And also updates the coordinates on the GPU. So the velocities and forces and coordinates, they never leave the GPU. The only thing that it does, to update the geometry, you need a new azimuthal angle, and so that bit happens on the CPU, and the controller happens on the CPU, because we find it's faster to not, because if you have 100 turbines, it's a for loop with 100 entries. It's faster to do that on the CPU typically, unless your controller is very heavy. Yeah. All right. So how is this done? So it's done in the Python bindings folder. The CMake list and so on, like how the compilation is set up is not entirely trivial, but maybe how you find where the interfaces are defined. So for each class that you want to bind to, or each function that you want to bind to, you have to define the bindings explicitly, and it's, for example, go to the actuator farm. So the actuator farm is also generally a bit, okay, maybe we start with the parameter. The parameter is a bit easier. So here we explicitly define the parameter. So this is the C++ class that we will use, that we will bind. This is the Python name that it will have. And then we kind of switch it around. We define that the Python class will have a method that's called setTimesTepEnd, and it will call setTimesTepEnd of parameter, and it will have this argument with this name. That's it. And then here for the parameter, we had to define quite a lot of classes, because you can set a lot of parameters. And then, for example, here you can also, you can also bind functions to the Python class that don't exist on the C++ class. So, for example, set the initial condition uniform. Here we define this is going to be the Python class, the Python method of the parameter object, and we just define a lambda function as the function it's going to bind to. And then here you can define what's happening in the lambda function, and then there we set then an explicit C++ function to call. And then we do the same thing with for the other more complex initial conditions. And I mean, when this, as I said, like the setup of it is a bit tricky. Once it's set up, it's kind of easy to extend, and it's very explicit in telling you when it breaks. Yes, we also have the base. In the basics, we also have, for example, some of the geometry. We had some of the geometry, I thought. Okay, we don't have the geometry. No, but for the grid generator. Yes, because the grid generator at the moment of the GPU works with its own objects. So if, for example, you have also all these objects here defined. So you can, I'm not going to try to put the sphere in again, but you could try to do it with the Python version as well. Also have all the probes. And yeah, so it's everything is defined very explicitly here. And then the final bit is the PyFluids minus TUBS. So these are then this is then the Python interface, how it's going to look. Great example. Yeah. So we know that we will have a let's say the class actuator farm, and on the Python side it will look like this. Python expects it to look like this. And then the dots mean just it's not implemented here. This is kind of like a header file in the C++ world. Yeah. No, this is done by hand. You can generate it automatically, but it's 99% accurate. But unfortunately, only 99%, and then you still have to do some things by hand. So I generated it once, and then I keep updating it, and then if I forget to update it for too long, I generate it again and then fix it again. It's not the ideal workflow. But, it's an interface, it shouldn't change so often. If there was more consistency. I mean, I don't know. I've never tried. I mean, but you would just have to define a folder CPU, and then also this init.py, and this is actually where everything that's on the top level of the package is defined.
But I saw some CPU
for the Python bindings. Yes, because I think that's actually the. There's also a Python binding to the Mu parser and everything. But I don't know. Yeah, Sven did all of this. So I don't know. I think they're built, though.
Other technologies used.
No, it's the same way. It's the same. It's the same way. So I copied this. I started from this and then extended it, basically. So I don't know, but I don't know what's happening in here. Yeah,
Question: when we use the Wi-Fi and we couple it with error elastic solver or something, how does it work? Like, does it run VirtualFluids for one time step, and then can I run two different solvers in one time step? How do they? Because
I mean, it depends. Actually, what we do at the moment is I will have to draw it again. I didn't prepare to talk about Wi-Fi so much. So there we also optimized for speed over accuracy, I would say. So if we have, here's VirtualFluids, and then here's Wi-Fi. We take, so this is time step t. We take the velocities, we interpolate them, and send them, well, we don't send them, but let's say we send them over to, no. How do we do it? We take them, did we do this? Yeah. We do it like this. So we take the velocities from one time step, and then we impose the forces from the last time step, and then we have this like staggered coupling. So actually, you know, normally Wi-Fi is much faster than VirtualFluid. So you can already pass back, well, you don't even pass them back, you just write them into the array. So we have actually two arrays of the force, and then we just flip them, we just switch them, right? We just alternate them. So this is VF, and this is Wi-Fi. So yeah, here you do the fluid, and here you do the turbine. And yeah, we write the forces into the array, and then the forces written into the array are imposed on the next time step, and in the meantime, Wi-Fi is already computing new forces based on the velocity from the last time step. So there's kind of a delay, but it's, you know, it's 100th of a second in time. So we believe, you know, that it's again the argument, you know, that smallest flow structures are smaller, are much slower than one time step. So we don't, there's virtually no change in velocity at the blades, so we don't notice. And also the blade hasn't moved a lot. The blade has moved at most half a cell typically at the tip. So nothing has changed from one time step to another. So they are much slower, so that's why we argue that this is fine. And we don't, like, we had it, you know, kind of sequentially in the beginning, that you can, you know, instead of taking this time step, we use this time like before, and there's no difference, we don't see any difference. And this way we can run Wi-Fi and VirtualFluids in parallel. The question is this really faster? And that I'm actually not so sure about, because both use the GPU, and VirtualFluids uses the whole GPU, so the GPU is anyways full. So in the end, actually, Wi-Fi is waiting on the GPU for VirtualFluids to finish. So I actually don't think this way is necessarily faster.
Okay.
So yeah, I'm actually, if I have time, again at some point, or someone else has time, I would like to implement, to run this in sequence again, because it also makes the programming much easier. Because then you don't have to use all this multiprocessing with two CUDAs, and like this way it has to do what's called context switching, which the GPU does not like. It takes time, and then you don't have to you only have one thread. You don't have to do context switches on the GPU, and you just run it. And my gut feeling tells me, and also looking at the profiling results, that this might actually be faster. But someone has to tie that up. Yes.
So does it make sense to run the Wi-Fi on the CPUs there? So they're actually
Good question. I think the way that it's currently implemented, probably no. Because I mean, it depends on. It always depends. For one turbine, probably maybe the CPU would be faster. but we always assume 100 turbines. Like everything is like, you know, nobody cares about a single turbine anymore. Like if you do 100 turbines with 240 meters diameter, then that's what we're going for.
But so, using the setup that you draw, it's possible to run virtual fluids for exactly only one time step, then wait for the input from the forces, and then continue for the next one time step.
Yeah.
Right, so it doesn't run through independently, but it... Like,
They do have to wait on each other,
right.
but ideally Wi-Fi is waiting.
Okay.
Yeah. And actually that's also what we see. That's usually Wi-Fi that's waiting. Yes?
Okay, you can tell for yourself, but I think like his question was related to air elastic coupling, kind of. But Wi-Fi is not air elastic. That would be a different, and then maybe depending on how small of a time step you have in your virtual fluids.
I mean, when
like see if I think because what you said was that it's 1-to-1 the way it is right now. Like so you get like the same air elastic time step as you would use in virtual fluid, so it would be still 1-to-1, but otherwise, yeah.
No, but I mean, yeah, you know, if you're fancy, you call it subcycling. It's a for loop, and you just said, yeah, run it 10 times, advance it 10 mini time steps, and then bring it back to the flow, because you're not gonna like, you know, you move half a cell at the tip in a time step. Like there's nothing. The time steps in LBM and in our elastic solver are much closer together than they are typically in an incompressible solver. So that also takes away some of the headaches. It solves all your problems. No, but what I did was like I subcycled open fast for 10 time steps or something like that, or however many it took, but it was only around that order, and yeah. But the problem that you're going to have is that your elastic solver is going to take much more time. Right. Because you know you have to run, yeah, you have to run 10 time steps of your elastic solver for one virtual fluids time step maybe. Yeah, it's going to be.
Why is that? Isn't time step smaller in virtual fluids than in the elastic?
And not in OpenFast at least. But OpenFast also has like a very, very small time step, I think, at least in the old version. It was yeah, where we can so here we need no, it doesn't print this. DT is 0.1 seconds.
Yeah.
So
the open fast one is like 0.0005.
Okay, that's more. Yeah.
That's small.
But 0.1, what is that the ABM in this case?
Yeah.
That's not so small.
Yeah, this is very large for LBM.
You always have to bring that together with the spacing.
Yeah, it's 10 meters. Yeah, so of course if you have it's still large. No, I think I think it's like 10 meters per second at the top. If you run with an actuator line. With an actuator line. Also, or with because the actuator line is...
Yeah, but the actuator line is normally limiting.
Yeah, exactly. But not with a disk. With a disk you could go larger.
If I see here, delta X is 10.
Yeah.
And if wind speed is 10, then that's a CFL of around 1. So this is 0.1.
No, 0.1. Because the time speed is, the delta T is 0.1 seconds.
Yeah, but then if you multiply by 10, then you get 1. Oh, yeah, it's 10 meters, but it's 10, yeah, of course. Yeah,
Yeah.
I see.
So it's the CFS number is 0.1.
Sorry,
Yeah.
Which is already, I mean, you're going...
I mean, we're pushing it.
Yes.
Yes. It works. I mean, yeah, we always assume Mach number of 0.1.
That's a good assumption.
So
No, okay, that was not my question. I forgot. Do you think if you have time that you can show us like where certain things in the code happens? Especially like I think the main thing with Wi-Fi would be to see like where you are reading the velocity and where you are sending back the forces.
Actuator farm. You mean here? The implementation of the actuator farm. You mean?
I mean, yeah, you know, I haven't.
So I mean, yeah, it's luckily very, very simple. I mean, we have the coordinates of the blade point, and then we have to. This one is actually a bit tricky because we have to find the cell. Because we have the coordinates, but then we need to find the corresponding cell, and because it's list-based, this is not. There's basically you don't have this mapping. You only have the other mapping. You only have from the index you can find the coordinate, but from the coordinate you cannot find the index. So we have to it's not written down in matrix or something like that. So we have to do. We kind of cycle through all the neighbors until we find the right one. So that can be a bit slow. And then we find all the neighbor indices. So we go to the neighbor that's like bottom southwest of our current of the actuator point. So
Do you have like the location from Wi-Fi?
yeah, Wi-Fi gives you a location, yes.
Yeah, and then you give this as input to
Yes.
VirtualFluid.
Yeah. Well, technically, yeah. Actually, Wi-Fi like VirtualFluids creates an array for the coordinates for all the points, and then gives this array to Wi-Fi, or the pointer of that array to Wi-Fi, and then Wi-Fi writes the coordinate in there.
Oh, okay.
So there's no copying or anything involved. So and then then Wi-Fi is like, okay, let's look at it. So we find the bottom southwest neighbor, which is, if you remember, the indirected. Well, we didn't actually talk about the indirect addressing, did we? Okay, so because you only have.
We talked a little bit about it. So we have this, we have this pointer chasing, and Martin also said that there is this one.
The BSW.
Yeah.
Yeah.
So, okay, so that is the one that Martin briefly mentioned, going in the diagonal direction backward. That is used so that by traversing the grid you can actually go to any other place.
No.
Yeah.
So exactly, we only know which is the next one in positive x, positive y, and positive z direction, and in negative of all of the directions. And so we have this. There we have to find. So there we have to kind of cycle. So this is iterating on the GPU. It's not good. Basically, GPU does not like. So we find the one that's in the inverse direction, kind of, and then from that we can easily find all the other ones. And then here we do trilinear interpolation of the velocity, and into this array, and this array is then the pointer to that array is then again given to VirtualFluids, to Wi-Fi, where it will then read these and compute new forces. And then the opposite is done here. So actually we.
May I just repeat my understanding so I don't get this? So you have the coordinates, and then you find the nearest cell to that.
Node, maybe?
What?
The nearest node?
The nearest node. You said cell like.
Yeah, I actually wrote cell, yeah.
I was getting, he was watching my face.
Okay, yes. Well, I don't know how this passed the review.
Yeah.
So did we find the nearest node?
Yeah, you find the nearest node, and this is just like you have it on the Wi-Fi side.
No, we are in VirtualFluids,
Yeah,
no
okay.
Wi-Fi.
And then you go there, and then you do the interpolation inside VirtualFluid as well?
Well, so at the moment I just want to. The input to the actuator line algorithm is the velocity, right?
Yeah.
So I have to get that velocity out of VirtualFluids first.
Yeah.
That's what I'm doing here.
Okay.
So I interpolate the velocities to the actuator points from the grid, from VirtualFluids on the nodes. I interpolate it to the actuator point.
How
Then
do you do it? Is it like from the
Here. I do a trilinear interpolation.
It's based only on the nearest node, or?
No, it's a trilinear interpolation of all the 4 neighbors. So,
4.
8.
8.
8.
Ah, yeah, 8 and 4.
8, yes. 1, 2, 3, 4, 5, 6, 7, 8. Yes.
Okay.
So yeah, exactly. We do trilinear interpolation.
I mean, is this why it's a cell? Because the cell, I mean, maybe.
Yeah, it's an interpolation. No. But I think we meant.
So because we have this interpolation cell. So when we talk about cells,
It's always 8.
In the idea in virtual fluids, I don't know whether this is now accurately here done, but in virtual fluids, the cell has the nodes on its corners.
Yes.
Yeah.
Yes.
I think this is a misnomer on our side.
Okay. There are many of them.
All right, and then actually in when you're working with the GPU, the question is always what do you parallelize, and you want to parallelize on the biggest array.
Yeah.
So when we apply the body forces again, basically the inverse. So we computed the forces. We have now this array of the component data, the forces x, y, z. We now have to bring them back. We now have to spread them, smear them in the domain.
Because you bring them exactly the force at the position when you put it.
They're exactly at the same point, yes. And again, we do that because time step small, nothing changed. We assume. So we parallelize here on the nodes in the fluid domain. So this is called per node. And then what the node does, because you have to either cycle through all the neighboring nodes, or you have to cycle through all the actuator points. So we cycle through all the actuator points, because there's going to be many more fluid nodes than actuator points. And actually also this way we can make it thread safe, right? Because now what I'm going to do is, I'm an actuator line, I'm a grid node. I go through all the actuator points and sum up the force contribution by each actuator point, and then it's thread safe.
All of it.
All of the actuator points that are close enough.
No, so you're saying like for each of the nodes you have in the domain, you take the contribution from that.
From each actuator point.
Actuator point.
Yes.
Okay.
So, but of course, we thought about this. So what we do is in the beginning,
Okay, bounding.
there's a bounding sphere. Yes. So we defined a bounding sphere. So if the actuator point is too far away, we don't take it. And also, where's the initialization now? In the bounding sphere initialization, we mark the points that are potentially affected by an actuator line, and we only go through those.
You do that once, right?
You do that once in the beginning,
Yeah, exactly.
and then you just keep them.
You have a list of.
There's a long list. For all the actuator points it could be, and then we can go, and then we check for each turbine, is the center of the turbine close enough? If not, then we just jump to the next turbine, because all the turbines must be discretized with the same number of actuator points. And so that way we jump through them quite quickly, and then you have your 96 points per turbine, typically, because you have 3 blades with 32 nodes. So in the end, we only cycle through 96 points in reality. So we optimize this a bit, and actually we also now have the option to not use a bounding sphere, but a bounding disk, because they even reduce it even further. And it even checks that you have all the points. So if your turbine is, but what could happen is that you place your turbine, you make a user error, and the turbine is placed so that the actuator points go outside of the domain, or they go into where the other GPU was, or something like that. But because we marked them beforehand, we will actually know in the initialization if your actuator line is going to go out of the domain or something like that, and then we cancel the simulation, and you have to start over. Well, I mean, you placed your turbine not high enough, you made a user error. You put the hub height at 0 meters.
You mentioned it could be an issue also if you're with multi-GPU.
Yes.
So we have to ensure that we also...
Yeah, each actuator farm must be initialized for each GPU. So No, for GPU you must, if you have different GPUs, you have to use different configurations for the actuator farms. We don't do this automatically. And so the limit is that the actuator farm must be on, like each actuator farm object must be on one GPU and also on one level, because we don't want to traverse levels. Level of refinement.
Yeah.
Because that's messy, and also like, you just don't do it. Like it's bad CFD. Yeah, in general, I think you don't need. It's not that hard. Like.
But if you have like so, but you still can do refinement on one single GPU.
Yeah, you can also do refinement among multiple GPUs, but yes.
Yeah,
But you can do a refinement on one GPU, yes, and then you place the actuator line, the actuator farm on the finest refinement level. So actually, that's an input to the actuator farm always. You can go to the header here. You always have to tell it which level you want it to be on.
Do you use refinement now?
But I mean, yes.
You use refinement.
I have used it before, yes.
Okay. No.
Well, you have to set the limiter on. But I mean, that's how I found out. Yeah, but other than that, it works really well. Works very nicely.
No, I'm asking because like I think like I guess maybe I remember wrongly, but that I recall that you said something that we don't usually do for the runs.
I mean, actually, it becomes less relevant, right? Because if the turbines get larger, but the boundary layer does not get larger, so at some point, it's the requirement. The smaller requirement is that you resolve the boundary layer, and not the turbine anymore. So, and I think that point is kind of the IEA 15 megawatt latest, because then you have 24 nodes across the diameter, 240 meters, so it would be 10 meters, and that is at least what you need to resolve a boundary layer as well.
So then in these cases you use a uniform grid.
And then you would use a uniform grid again, yes. But yeah, that's yes.
Fantastic.
So are there any questions? Yes.
Did you have use special container for this Python binding?
No, just now it doesn't work. I think Martin has already pushed the update, or because CMake was updated last night. Now the 4.0 is not backwards compatible apparently, but it's the normal container. Yeah, yeah, you have to change this line 31 that it mustn't use CMake.
I mean, I just check if Python container exists.
There's a okay, but no, but there's a Python in the container. It's 3.11, which is not so nice. But
The other question, the API stuff.
mm-hmm.
Can you show how you can start API Python or Python with API?
Yeah. To run like an MPI, you just run MPI Python and then whatever. It's very like it's really the same, yeah. But it's the program that you call is always the Python interpreter, and then the input file to the Python interpreter is then the Python script. So I would say Python and then actuator line. Which Python?
We have then in this case 2 Python processes.
Yeah. Then line.py, is that right? Yeah, I always forget that. What was it? Allow run as root. Ah, no, it has to be. Okay, I don't know. I can't fix it right now, but. It was there earlier. Because I could. Bin Python 311.
Some competition. There appears to be some competition.
I'm still recording.